Math Humans. We're going to do 4.4 today. It's our last section in Chapter 4, talking about our growth and decay models. Today we're going to be talking about the natural and the logistic growth. Our objectives are that we're going to explore these two new models. So the first one that we're going to talk about today is the natural growth model. So that equation is P of t is equal to P of 0. This is the new piece raised to the kt. So we still have our population in terms of time. P of 0 is still the initial population. K is going to be our growth rate. And for this one, if k is greater than 0, meaning that k is positive, then that's going to mean that the function is growing. And if k is less than 0, meaning that it's negative, then that means we're going to have decay. T is obviously going to be time. And then E is a constant. And it is an irrational number. And let me show you on your calculator. So right here, up above your divided sign is E. So if I do second E, you can see E on your calculator, and I hit enter. The value of E is 2.718, etc., etc. And it is an irrational number. So this is just a constant. It does represent a ratio of numbers. And we're actually not going to talk about what ratio or where that number comes from, but for right now, all you need to know is that E is just a button on your calculator, and it is an irrational number. Alrighty, so I think that is all we need to know. It's still an exponential growth or decay, so its graph is still going to look like this. So let's just jump right in and do an example. So for our first example, it says when a certain drug is administered to a patient, the number of milligrams remaining in the bloodstream after T hours is given by the model. And so here is our decay model, because notice it's negative. How many milligrams are in the blood after 2 hours? So I'm going to write our model down here just because it's easier to see, maybe instead of having it inside all the words. And I want to know what happens after 2 hours, so P of 2 is going to equal 40e to the negative 0.25 times 2, and I would push buttons on my calculator, so I'm going to clear all the things that are there. So I'm going to do 40 second e, and I'm going to raise it to the negative 0.25 times 2. Remember, if you are using some of the older little black calculators, you need to be really careful that you put your entire exponent in parentheses. So I'm going to go outside and hit enter. And so after 2 hours, my drug concentration is 0.26 milligrams. And so then I would report my answer well, so 24.26 milligrams. So that wasn't too bad. We're just using our calculators to help us solve those problems. All right. For the next example, number 2, we're going to have an ant problem. So on the first day of May, Bob discovers a small ant hill in his backyard with a population of 100 ants. I think that's entertaining because how do you count a population of ants? Colonies of ants have a growth rate of 240% during the first 4 years. How many ants will Bob have next May, and then how many in 5 years? Okay, let me turn my mood music down a little bit. Alrighty, so if we have our model, P of t is equal to P sub 0 e to the kt, we can substitute in everything we know. We know that our initial population is 100, and I'm going to do this over here. 240% is going to be 2.4 when you turn it into a decimal. And if I took the 240 and divided it by 100, that would be where the 2.4 comes from. So e to the 2.4 times t. So that would be my model. We always want to make sure that we record the model that we're using. So then the next question, it says, how many will he have in May? So May is going to be 1 full year. So P of 1 is going to equal 100 e to the 2.4 times 1. And again, I would put that in my calculator. And when I do, I get 12151.04. Now, because we're talking about creatures, we can't have 0.04 of an ant. That would be gross. So instead, I'm going to round. This is a small number, so I'm going to round down. And that would be how many ants I have after a year. Well, the next question is, how many ants am I going to have in 5 years? So it's going to be 100e to the 2.4 times 5. And when I put that number in my calculator, it's going to be an amazing number. It is 16,275,479 ants. That's a lot of ants in 5 years. Alrighty, the next thing that we're going to talk about is a new growth model, and it's actually a really cool growth model, and it's called the Logistic growth model. So the equation looks really scary, but it's actually not. So the thing that you'll notice is that there is no piece of zero. So the initial population is not part of this formula. M is a cool component of the equation, and it is called the carrying capacity. And what that means, it is the limit to either growth or decay. Okay, so I'll talk about that in a little bit more detail when we talk about the graph. Okay, in this particular model, C and K are both constants. So C and K are constants. And then T is going to represent our time. Okay, this is important because this is a very unique graph, and it's one of the most unique graphs because it has 2 horizontal asymptotes. So it's going to have 2 different horizontal asymptotes, and the graph is going to look something like that if it's growth. So this carrying capacity is the top asymptote, which means that that's going to limit how high the graph can go. And if it were decay, okay, can I draw that? Maybe that hurts my head a little bit. Oops, I'll draw it backwards. There we go. That's easier. So, or it would be the limit of what's going to happen on the bottom end. Typically, we talk about growth for this particular model. So oftentimes, M is going to be a limiting factor, and it can be for a variety of reasons. Maybe it's because of a water supply. Maybe it is because of the number of predators. So M is going to be whatever stops the growth of the particular function. Alrighty, so let's go and look at a couple of examples. This is really important to remember. This will be something that we have to solve for, and we'll talk about doing that math in a little bit. So for our next example, example number 3, it says the population of an endangered bird series on an island grows according to the logistic growth model. We want to find piece of zero because remember it's not given, and then we want to know the population of birds in 5 years and 150 years. So let's talk about the equation first. This 3640 is the carrying capacity, and that means that is going to be the maximum possible population of birds. And maybe because we're on an island, it's because that's all the food sources can support. Maybe it's because the natural predators will eat them if the population gets past that much. So the first task says, what is piece of zero? Well, remember, piece of zero is the initial population. That also means it is the population when time is equal to 0. So because this number isn't in this equation, we're actually going to let t equal 0. So p of 0 is going to equal 3640 divided by the 1 plus 25e to the negative 0.04 times 0. Well, negative 0.04 times 0 means this is going to be e to the 0. And remember that anything raised to the 0 power is 1, so this becomes 1. So now the math becomes 3640 divided by 1 plus 25, so it's 3640 divided by 26, and that's going to yield 169.6, but remember we're talking about creatures, so we don't want to have 0.6 of a bird, so we're going to say that P sub 0 is equal to 170 birds. Remember that you always need to include the unit. So now the next part of our problem said find the population in 5 years and 150 years. So P of 5 is going to equal the 3640 divided by 1 plus 25e to the negative 0.04 times 5. So let me show you how to enter that on your calculator and things that you need to be careful with. I'm going to zoom in just a little bit so we can see our calculator better. Here's what you need to be careful when you're doing the logistic growth model. I'm going to enter my carrying capacity divided by the denominator has to be in parentheses. So it's going to be 1 plus 25 second e raised, and I have a negative 0.04 times 5, and then I'm going to close the denominator, and I'm going to hit enter. So did I do that right? I think I did that right. 3640 divided by, yes. So in 5 years, I'm going to have 170 birds, okay? So they're not going to grow much in 5 years because we kind of started with 170 and so now we're here, okay? And actually, let me just check my math on the other one and make sure I didn't make a math mistake. Clear, 3640 divided by 26. This is my mistake. This is 140 birds, my bad. Okay, so we're going to change this number to 140. I knew something had to be wrong. So it grew by 30 birds in 5 years. So now let's look at what happens in 150 years. So it's going to be 3640 over the 1 plus 25 e to the negative 0.04 times 150. And when I do that math, so let's do it in our calculator. So I'm going to do the 3640 divided by parentheses 1 plus 25 second e raised to the negative 0.04 times 150. And then I'm going to close my parentheses and I'm going to hit go. And now I have 3427.60. Remember, I can't have a part of a bird because that's just gross. So we're going to round that number to be 3428 birds. Okay, and I'm going to change my thing there. So then I'm going to report, well, P of 150 is equal to 3428 birds. So notice that our carrying capacity is 3640, and in 150 years we're approaching that capacity, but we're not quite there. So at some point, the population of birds will actually stop growing. Alrighty, I have one more example for us. Example number 4, a fish hatchery has a population modeled by the logistic growth model. What is the carrying capacity of the fish hatchery, and how long will it take for the population to reach 6,000 fish? So here's our model. Notice that this is going to be my carrying capacity. So my carrying capacity is going to equal 12,000. And remember, if you think about the graph of the logistic model, that is that top horizontal asymptote, meaning that the population's not going to exceed 12,000. So the second one is going to be interesting. We're going to actually approach this 2 different ways. We're going to do it algebraically, and then I'm going to show you how to do it graphically. Both will give you the same answer, but it's two very different approaches. So the first one says how long, which means that we are going to solve for time. So I'm going to set 12,000 over the 1 plus 11 e to the negative 0.2 t equal to the 6,000, and we're going to solve for t. So the first thing that we're going to do is we're going to cross multiply, but we're not going to distribute. So I'm going to get 6,000 times 1 plus 11 e to the negative 0.2 t is equal to 12,000. Okay? The next thing that I'm going to do is I'm going to divide both sides by the 6,000 because I need to isolate my t. So I get 1 plus 11 e to the negative 0.2 t. 12,000 divided by 6,000 is 2. The next thing that I'm going to do is subtract 1. So I'm going to write equals 1. Okay. Now I'm going to divide by 11. So e to the negative 0.2 t is equal to 1 divided by 11. And I divided both sides by that 11. Okay. Because I have a 2t in the exponent position, I'm going to take the log of both sides. So if we take a little side trip, I'll do it over here. The log base 10, if you'll remember, was called a common log. Well, a log base e is called a natural log, hence the natural growth model. And instead of writing log base e, we write ln, and that is a button on your calculator. So since I have an e, I'm going to take the natural log. It's going to go out front. So I'm going to take the natural log of both sides. So negative 0.2t natural log e is the natural log of 1 divided by 11. And we're not going to push buttons on our calculator yet. The natural log of e is 1. So you can just take my word for that, or you can push buttons on your calculator if you don't believe me. So I'm going to divide by a negative 0.2, and I'm going to divide by a negative 0.2, and I get time is equal to 11.99 years. Okay, and let me show you that in my calculator. So I'm going to do the natural log of 1 divided by 11 divided by a negative 0.2, and there's my 11.99 years. So that's a lot of algebra. So sometimes, instead of doing the algebra, we attempt to solve the problem graphically. So I'm going to go back to this equation. So I have 12, 1, 2, 3 over 1 plus 11 e to the negative 0.2 t is 6,000. Just like we've done with other ones, this is going to be y1, and this is going to be y2. So let's go to our handy-dandy grapher, and let's kill everything that's there. So I'm going to enter 12, 1, 2, 3 divided by parentheses 1 plus 11 second e raised to the negative 0.2 times x, and then close my, except I missed this part, raised to the negative 0.2 times x, and then I'm going to delete those guys, put in my parentheses. I think I have it right now. And then I'm going to put 6,000 as the other equation, and I'm going to do a zoom 0 for a zoom fit. Whoop. Okay, so there goes my logistic growth function, and there is, this is the y equals 6,000, so I need to zoom out a little bit, zoom 3, enter. Here comes my logistic growth function. And there comes my horizontal. So the goal is to find that point of intersection. So second, calculate, 5 for intersect. And I am going to trace a straight line because the shortest distance between 2 points is a straight line. Enter, enter, enter. And there is my answer. There's the 11.97 years. So my time is equal to 11.99 years when I round that number. So remember that if I solve a problem graphically, then I would sketch the graph, and so here would be my sketch, and then I would label that time is equal to 11.99. And that's it for today. Thanks for being patient, and I'll see you soon.